we have Ariel Kleiner, who will tell us all about statistical hypothesis testing. We know it's important.
Excellent. Can you guys hear me?
Yes.
So, so my name's Ariel Kleiner. I'm a PhD student at UC Berkeley. I'm going to talk about quantifying uncertainty of estimates, which hopefully by now we're pretty convinced that this is an important problem. Before I continue, let me say this is joint work with Amit Talwalkar and Purna Sarkar, also at Berkeley, as well as our advisor, Mike Jordan. Great. So before I continue, raise your hand if you are familiar with the bootstrap. OK, that's pretty good. It's almost like we're at NIPS. So our setting here is going to be, or our goal is pretty simple but very general. So we're going to observe n data points. For today, there'll be IID, but that can be relaxed. We're forming an estimate, theta, and we'll call the estimate based on n data points theta hat n. That can be something as simple as a mean or as complicated as a classifier. And our goal here is, given this estimator theta and a set of n data points, we want to compute an assessment C of the quality of theta hat n. And that assessment could be a confidence interval, confidence region, a bias, a risk, whatever you want, right? The point is we're quantifying our uncertainty, or more generally, assessing the quality of our estimate. And so the reason this is important is, for example, if we're training a classifier, we train a classifier based on 5 data points, right? We should probably be less certain that this is a good estimate than if we had trained our classifier based on 1,000,000 data points. Obviously, we have that intuition, but it's very useful to be able to quantify that. For example, if we want to do hypothesis testing, is one actually great example, right? So we want to be able to do this in a great deal of generality, and so we want a procedure which can take this theta and quantify its quality, assess its quality, and we want this procedure to be accurate. We want it to be automatic. It shouldn't depend on the internals of theta, right? We don't want to have to do deep analysis of every new estimator that we want to treat, and we want it to be scalable. We want it to scale up to large amounts of data, well, because otherwise I wouldn't be speaking in this workshop. So, OK. Great. So existing procedure. If you look at, statisticians have been thinking about the problem of assessing estimator quality for some time. And so there are procedures to do this. And in fact, statisticians have been known to use computers. And so they've developed computational procedures even for doing this. The issue with existing procedures is that, in general, they don't satisfy all 3 of these criteria. We have procedures which are very accurate and automatic, but not so scalable. More scalable procedures which are not as accurate and automatic. And so I'm going to talk today about work we've done on creating a new procedure that is satisfies all 3 more than existing procedures do. OK, so how would we go about creating such a procedure? Well, if we were God, if we could do sort of the ideal thing, right, we would simply, to quantify the quality of an estimator theta, we would run repeated experiments, right? We would repeatedly observe independent data sets of size n. For each of them, compute theta. We'd get a collection of thetas, and we would quantify the uncertainty in those, right? We could compute their standard error, compute a confidence region. And drawing this schematically, right, we have n independent data, a number of independent data sets, each of size n. For each, we compute a theta hat, take those theta hats, and assess their variability. More generally, some quality assessment. The reason we can't do this is we only observe one data set of size n in practice, right? So that seems to leave us in a bit of a bind. So as I said, statisticians have given some thought to this problem. And so in 1979, Brad Efron at Stanford proposed the bootstrap, which many of you are familiar with. So I'm going to go pretty briskly through this. But the point is we just basically simulate the ideal process that I just went through on the previous slide. So basically, we use the observed data to simulate data sets of size n by resampling with replacement. Right, we do this resampling process repeatedly. On each resample now, we compute theta hat. Now the theta hat has a star because it's computed on resamples from the original observed data. We take the theta hats and compute our uncertainty quantification. And so schematically, that looks like this. Very similar to the previous slide, right, except that now we start with a single observed data set without stars. We generate multiple simulated data sets of size n, compute the theta hats, and combine, right? This is obviously very simple. It turns out to be very powerful, right? Because number one, we're not using any information about the internals of theta, right? We just need to be able to compute the theta. So functionally, right, somebody could just give us a computer program that computes theta and not tell us exactly what's inside of that, right, as in from the standpoint of implementation. It turns out to be very accurate in very general settings. But what about the scalability? What about the computational issues? So let's talk about that a little bit. So the key fact here is going to be that the expected number of distinct points in a bootstrap resample is about 0.632n. So about 63% of the points in the original observed data set will appear at least once in a given bootstrap resample. And the reason for that is, again, that we're resampling with replacement, right? So some data points will appear more than once in a resample. Some will not appear at all. The second key point here is that the resources required to compute the estimator are generally going to scale in the number of distinct points that you feed to it, right? The reason for that is that if you have replicated points in the data set you're feeding to an estimator, right, you wouldn't actually physically replicate them. You just attach weights to them, right? And most of the estimators that we care about, right, have this property that they can operate on this kind of weighted representation. Things like regressions, kernel methods, M-estimators in general, really, and beyond. So again, right, so when we're running the bootstrap, we would use this weighted representation to avoid the physical data replication. The problem is that if n is big, and we're doing big learning here, right, so n is expected to be pretty big, 0.632n is also going to be very big, right? So concretely, if I start with a terabyte of data, then each resample is going to have size roughly 632 gigabytes. And I have to do this repeated computation of theta on data of size 632 gigabytes. Okay, so that's not so great because I'm going to have to compute on a few hundred resamples. And you might say, okay, well, I'm computing on these resample. Okay, well, before I do that, let me just write that out in explicit pseudocode, right? So let's say 300 resamples for each of them. I resample about 600 gigabytes, compute theta on each resample, combine. Sorry? Okay. So we're doing this repeated computation on large amounts of data. You might say, okay, I'm computing on each of these resamples independently, right? Why not parallelize this, right? And the reason is that within each iteration, I have to touch a different set of 600 gigabytes of data, right? So are you going to ship 600 gigabytes of data to each of 300 different compute nodes? That's not so great. You could imagine going through a great deal of pain, potentially, to try to make this work. But we're actually going to give a procedure that makes this trivially easy to parallelize, or much, much easier to parallelize. Okay. Okay, so just to summarize, the Bootstrap has many virtues. In particular, it's accurate for a wide range of theta. It's automatic, as we've said. But it has this unfortunate need to repeatedly compute on large sets of data. And it's difficult to parallelize that computation across the resamples. Okay, so we want to overcome these disadvantages. So how do we do that? Well, we go back to prior work. Why not? If we do that, we go back to prior work, we'd come across something called the B out of N bootstrap. Also very simple, very related to the bootstrap. And the idea here is that we just reduce the size of our resamples. Rather than resampling n points, resample b less than n points, right? And just do what the bootstrap does. So resample b less than n points repeatedly with replacement, compute theta on each resample, combine them. But we're not done yet. And the reason is that we're computing theta hat sub b's here, okay? And b is less than n. So if b is less, so an estimator computed on less data is generally going to be more variable, right? So this c that we're computing in step 3 is based on theta hat b's. It's going to be too, let's say if it's a CI, a confidence interval, it's going to be too big, right? So we need to rescale it, basically. And the way this is done is you need to analytically rescale or analytically correct based on prior knowledge of the convergence rate of theta. So what we've gained here, so actually it's worth saying this was invented by statisticians without computational issues in mind. It was created, this procedure was created to handle statistical edge cases where the bootstrap is known to fail. But it is more computationally favorable, clearly, right? We're computing theta repeatedly only on potentially much smaller subsets of the data. But it turns out empirically that the accuracy is quite sensitive to the choice of b. If b is too small, the b out of n bootstrap will fail. And also, while still fairly automatic, now we have to do this analytical rescaling based on convergence rates, and so we've given up some of the automation. I should say also, in the interest of thoroughness, that there's another procedure called subsampling, very related, which the only difference is that subsampling, rather than resampling B points with replacement, it subsamples B points without replacement. Okay? And behaves very similarly to the B out of N bootstrap. Actually also tends to fail for very large Bs, so in general has somewhat worse behavior. So we're really going to be talking about, when we talk about prior alternatives to the bootstrap, we'll talk about the B out of N bootstrap. Okay. So just to drive this home, this issue about brittleness of the accuracy of B out of N bootstrap, I'll show you some empirical results. This is going to be a linear regression, 100-dimensional linear regression, n equals 20,000 data points. This is going to be synthetic data, which is necessary here so that we know the ground truth, right? We need to know the true CIs for our estimator in order to do the evaluation. You'll trust me that this is, we're generating things from various data generating distributions. We're doing least squares estimation. Our XI, our quality assessment here, is marginal confidence intervals on the components of the estimated parameter vector. And we're evaluating based on the confidence interval sizes, on the confidence CI widths, right? So basically, the bootstrap outputs a confidence interval. We calculate its width, compare that width to the width of the true confidence interval. Okay? For the B out of N bootstrap, we're going to take B equals n to the 0.5 up to n to the 0.9. And the results you'll see are pretty robust to the choice of data generating distribution. We can do this with estimating misspecified models, similar results. Okay? And here we go. So what you're seeing here is on the y-axis is relative error of the output of the procedure. So again, how far is the width of the CI outputted by the bootstrap from the true width of the CI? Right? So are we getting the appropriate quantification of the uncertainty in our estimator? Okay? So lower is better. The x-axis is time. So as we run the procedure, as we process more and more resamples, in the case of the bootstrap, what happens to the relative error, right? So the bootstrap here is the blue line with circles. As we process more and more resamples, it does better and better, right? Converging to nice low relative error. The other dotted lines are all the B out of N bootstrap for different values of B. And so what we see is that for the larger values of B, for B equals n to the 0.7 and higher, the B out of N bootstrap is behaving very nicely. It's converging to low relative error faster than the bootstrap, right? Showing nice computational gains. The problem is if B is too low, n to the 0.6 or lower, right, it's failing. It's not converging to low relative error. This is not good, right? Number one, we want to make B as small as we possibly can. Number two, how do we know where this threshold is, right? How do we know that n to the 0.6 is the cutoff? Okay, so what we'd like to do is at the very least reduce this threshold. Well, we would also like to keep things more automatic. We want to eliminate the rescaling that the B out of N bootstrap has to do. While maintaining the scalability. Okay, and so that's exactly what we do. So we're proposing a new procedure called the Bag of Little Bootstraps, or BLB. Okay, and what we're going to do is only touch small amounts of data at a time while maintaining much greater robustness to the choice of B. Okay, so we start by repeatedly subsampling B points, B less than N points without replacement from the original data set. So we have a number of these subsamples. For each subsample, we then run the bootstrap on that subsample. Okay? So we take the subsample. Given a subsample, we resample N points with replacement. So we've gone from N down to B, and then we resample back up to N. Okay? We do this resampling repeatedly for each subsample. So for each resample, we compute theta hat. Given the resamples, we combine the theta hats to get a XI, let's say a confidence interval. So now what we've done is for the particular subsample that we're processing right now, we've obtained a CI, or a standard error, what have you. Okay, and now we have one of these quality assessments for each subsample. How do we get a final single quality assessment? Well, we just average. Okay, so if it's a CI, we might average the boundaries. If it's a standard error, we just average the standard errors. Okay, so I'll show you in a couple of slides that this is more accurate than alternatives like the B out of N bootstrap. It's, I think, clearly by construction automatic, right? Like the bootstrap, we're not using any analytic rescaling. We take the theta as a black box, right? You just need to be able to compute it. How about the scalability, right? So we are subsampling B from n points, but now we're resampling n points. So are we still scalable? The answer is yes, and here's why in one slide. So here's the schematic representation of that, just to drive this home, right? We start with a data set of size n. We take multiple different subsamples. For each subsample, we run the bootstrap on the subsample. That's what the rectangular box is. That gives us a xi for the subsample. Multiple x's, we combine them by averaging. Okay, so let's talk about the scalability of BLB. So remember that the key thing is the number of distinct points that we're feeding to theta. For each computation of theta, how many distinct points are being exposed to it. And the key thing here is that each BLB subsample has only B points, B less than n points. As a result, each BLB resample also has at most B distinct points. Okay, and you can choose B to be much less than n. And an example here is that if we start with n equals 1 million, let's say data point size of a megabyte, roughly, and we're going to take, in this example, b equal to n to the 0.6. So 1 million times a megabyte is a terabyte, right? So just like our earlier example. Now BLB subsamples and resamples are going to have at most 1 million to the 0.6 points, so roughly 4,000 points. So a BLB resample will have size at most 4 gigabytes. So we've gone from a terabyte down to 4 gigabytes. So that's pretty good. How do we compare to the bootstrap? So that's compared to the full data set, right? We started with a terabyte in the full data set. Resamples have 4 gigabytes. A bootstrap resample, remember, has size 632 gigabytes, roughly, an expectation. So we've gotten a 2 order of magnitude reduction. That's not too bad, I would say. So let's summarize this. So like the bootstrap, we're accurate for a wide range of theta. So basically, we can show actually that you get consistency and good convergence rates, favorable convergence rates under the same conditions as the bootstrap. We're as automatic as the bootstrap. How do we go beyond? Both the bootstrap and the B out of n bootstrap are subsampling. So beyond the bootstrap, right, we're explicitly controlling the amount of data used to compute the estimator at each stage, right? So theta only touches at most data of size b. And b over n can actually go to 0 as n goes to infinity. Right? So in general, we're going to take b to be a slowly growing function of n, such as n to some power less than 1. We're more robust than the b out of n bootstrap in subsampling to the choice of b. I'll show you empirical results on that in a second. We're generally faster than the bootstrap, even in the serial setting. And so we require less total computation and more easily parallelizable. Right? Because now, let's take our example. We started with a terabyte of data. We're down to 4 gigabytes. You can put 4 gigabytes on a single node. Putting 600 gigabytes on a single node is a lot more problematic. Okay. So, empirical results. Again, y-axis is relative error, so lower is better. X-axis is time, number of iterations of the procedure, number of resamples, or in our case, subsamples processed. So the bootstrap is, again, the dotted blue line, converging to nice low relative error as we process more resamples. BLB is all of the solid lines for different values of b, and now you see that for all of the values of b considered, n to the 0.5 up to n to the 0.9, we are converging to nice low relative error, much faster than the bootstrap. Okay. Now, these are results for this linear regression setting. We don't have that much time, so I'm not going to go more deeply into the empirical results. We've also done experiments. As I said, these results are robust to the choice of data generating distribution, to whether or not you're estimating a misspecified model. We've also done results on logistic regression. That appears to be a harder problem, but the message is still the same. Basically, we are still more robust, significantly more robust than the B out of n bootstrap to the choice of B. But of course, BLB is not magic, and of course, there will always be a sufficiently small value of B such that things break. The point is we push that significantly farther down. And we also eliminate the rescaling issue. Okay, so this just puts the two plots side by side, the two plots you've seen so far, right? So remember, before we had these for the lower values of B, things not converging. BLB converges nicely. I'll finish, since we're running out of time, by saying that while I'm not discussing it here, we have some nice theoretical results showing that BLB basically shares the bootstrap's favorable statistical properties, consistency, fast convergence rates under the same conditions used for analyzing the bootstrap. And so just to summarize, remember our original goal, right, was a general procedure for quantifying or assessing estimator quality that was accurate, automatic, and scalable. Right, the bootstrap is very generally accurate and automatic, not very scalable. Other prior works, such as the B out of N bootstrap, is more scalable, but suffers on the accuracy and automation front. And so we're providing a new, and I would say more favorable combination of all three for the large data setting. Thanks. Right. So in these experiments, we were doing 100 resamples per subsample. And the number of subsamples you need depends on the value of b. So for larger values of b, you need fewer. So for like b equals n to the 0.9, you only need 1 or 2 subsamples. For b equals n to the 0.5 or 0.6, you might need, I think, 10 to 14, let's say, 10 to 20 subsamples. And it's also worth saying that you can use fewer resamples depending on your quality assessment. So for estimating things like quantiles and confidence intervals, you need more resamples. If you're estimating something like a standard error, maybe 25 resamples might suffice. I mean, the total number of estimator computations is the number of resamples times the number of subsamples. Well, you can run the resamples in parallel, right? So every estimator computation here could, in principle, be done in parallel. And so one of these guys might need a few hundred estimator computations, but now they're estimator computations on, say, 4 gigabytes of data rather than 600 gigabytes of data. So, yep. Yeah. Well, can you speak a little bit more loudly, first of all?
I'm just wondering about that component.
Yeah. Yeah, so the black line at the top here is b equals n to the 0.5. Yeah. And the green line here is n to the 0.6. I mean, it's a good question. To be honest, I don't have a concrete answer to that. It's worth saying, right, that the jump between n to the 0.5 and n to the 0.6 obviously is not, you know, like linear in the difference between 0.5 and 0.6, right? So, you know, I mean, it's a substantial reduction in the amount of data you're looking at to go from n to the 0.6 to n to the 0.5 is one answer. It's also worth saying that in these experiments, right, d equals 100, n equals 20,000. 20,000 to the 0.5 is roughly 140. So if you were to go really much lower in terms of choice of B, you'd be like hitting up against the statistical, essentially like a hard statistical barrier on the reduction you can have in the size of resamples and still have good performance, essentially. So, yeah.
I think you're using an unbiased estimator.
In this case, it is. So we haven't done those experiments specifically, but there should be no particular reason you should have any particular problem like that. In fact, you can use the bootstrap to measure bias, actually. Like you can actually assess bias using the bootstrap. So I can say certainly from the standpoint of theoretical analysis, it doesn't make a difference. It's fine. Yeah.
All right. One more question. What applications do you have in mind for this kind of scales?
I mean, so to be honest, we didn't start out with a particular application in mind. I think one nice thing about these techniques is that they're so generically applicable. Yeah. I welcome you all to create wonderful applications of the Bag of Little Bootstraps.
This is hard enough. We're done with the first day.
Thank you.